Hello everyone, this is Mirzai from Cal Poly Pomona, and in this lesson we're going to look into another example of writing the dual programming of a linear programming problem. This time we're going to look at example 7.2 of your textbook. As you learned earlier, we can write the dual programming of a linear programming problem in two ways. Either we normalize it and then write the dual of the normalized problem, or we skip the normalization step and write the dual programming directly. You can choose any of these two methods and stick with whatever that is more convenient for you, but I'm going to show both ways in here. So the first method that we're going to cover is normalization. So if it's a min problem, in a min normal problem, everything should be greater than or equal. And therefore, we should revise the first and second constraint of this problem because they are not in the form of greater than or equal. So let's go ahead and do that. For the first constraint, I have to multiply it by a -1 to make it a greater than or equal equation. Now for the second constraint, to normalize, I have to create two inequality from the existing equation. If I write 2x1 plus x2 greater than or equal to 3 and 1's less than or equal to 3, then the combination of these two equations is the same as 2x1 plus x2 is exactly equal to 3. So if I replace that equation with these two equivalent inequalities, the problem is the second constraint is not in the form of normal min problem. So I have to multiply it by a -1 to normalize this equation. The third equation will be exactly the same. And now we can put everything together and write our normal min problem, which includes the first equation that we normalized, this one, and the last equation. All together are shown in this normalized min problem. Now, how can I write the dual programming of a normal min problem? Normal min problem, dual programming is going to be a normal max problem. To write the dual programming, instead of writing the coefficient as a matrix and then transposing it and multiplying it by y variables, what I'm going to do, I'm going to write one variable associated to each of the constraints here. Then my first constraint is going to be multiplication of these variables with the coefficient of x1. So basically you're going to write one equation for each column. So my first equation is going to be -y1 plus 2y2 minus 2y3 plus 2y4, which I wrote here. The second equation is going to be multiplication of y's with the x2 coefficient, which is going to be -y1 plus y2 minus y3 plus y4, which is written here. For the third one, I have to multiply y's by these coefficient here, which is going to be -y1 plus 0y2 plus 0y3 plus 3y4, which is here. So I skip writing 0y2 and 0y3. Also, don't forget to write all the y's are greater than or equal to 0. Now, because it's a min normal problem, the result is going to be a max normal problem. So the objective function is going to be a maximization where the coefficient of y is coming from the right hand side. So I'm going to go ahead and write my equation for the objective function, which is -2y1 plus 3y2 -3y3 plus 3y4. And then because it's a max and it's going to be normal, everything should be less than or equal in the constraints. And the right-hand side here comes from the objective function coefficient. You can write 4, 4, 1. So it's very easy to normalize and then write the normal max or min problem given your primal problem, because it's very standard to figure out the sign for the constraints as well as your decision variables. However, if you choose to use the second method for directly writing your dual from your primal, we can also explore that. So this is the same primal problem that we saw earlier. Now I'm going to write its dual without going through the normalization step. To do that, I write the equation for the constraints the same way that you saw earlier. I'm going to define variables for each constraint. This time we only have 3 decision variables because we only have 3 constraints. So the first equation comes from here, 1y1 plus 2y2 plus 2y3. The second equation comes from here, y1 plus y2 plus y3. The third one comes from here, 1y1 plus 0y2 plus 3y3. Now, I have to define the sign for the decision variables. So for a min problem, the standard format is greater than or equal. So the other two constraints do not have the standard format. So only y associated to the third constraint is going to be greater than or equal to 0. For the other two, you're going to follow the table that I gave you earlier. So the first constraint is less than or equal, and we are in a min, and in less than or equal, the variable is going to be negative. So you're going to write y1 as negative. y2, you have a constraint that is equal to some value, so it has the equal sign. So your variable associated to that is going to be unrestricted in sign. And the third variable has the normal format. This is the sign of your variables. Now I have to define the sign for my constraint, and they are defined based on the sign in the variables in my primal problem. All variables are in form of greater than or equal. Therefore, all the constraints are going to be in the form of less than or equal. We put them here. It's a max problem because it's the dual frame minimization problem. The rest of it is very straightforward. The right-hand side here becomes the objective function coefficient, and objective function coefficient here goes to the right-hand side. Now the question is this dual programming equivalent to the one that we found out from the first method where we did the normalization? The answer is yes, because if you remember, in linear programming problem, we always want all the variables to be greater than or equal to 0. So to adjust the y1, we have to replace it by negative y1 prime, for example. And to fix the y2 being unrestricted in sign, we have to replace it with y2 prime minus y2 double prime to fix the issue and create the unrestricted sign variables with two positive or greater than or equal to variables. If you do these replacement in the equations of this problem, both in the objective function and the constraints of the problem, you get to this, to the initial dual programming problem that we wrote. As a result, these two equations are exactly the same. Now, which one you choose to pick for solving questions in your homework assignments, you can choose whatever method that seems easier and more comprehensible in your case. Thank you for watching.